Hey Wheaton North, Mr. Yergler here. Let's talk about half-life reactions. The half-life of something is, simply put, the amount of time it takes for half of it to decay. This is usually used in reference to like a radioactive isotope decaying over time. They use this in obviously carbon-14 dating and a lot of like geological processes. They use half-life a lot. The couple main things to point out. It's often represented as T half, and it's going to be a first order reaction for all of our purposes. Every time it's half-life, it's first order reaction. It is possible to have half-life be done as a second order reaction, but it's a little bit less common. The rate of the decay decreases, and I want to kind of be really clear here. Let's take a look at this graph. Notice that the x-axis is the number of half-lives, right? And so if we start with one molar concentration, the half-life is the amount of time it takes for half of that to be depleted. Okay, so if we were thinking of this in a chemistry reaction context, this would be the amount of time it takes for half of our reactant to disappear and form product. And this is labeled as one half-life in this case. The exact same amount of time then is required to take this amount and cut that in half, right? And so this is gonna be a first order reaction, because as we decrease the concentration, the rate of decay is decreasing, but I don't want you to get confused. The time it takes for half of the sample to disappear is always going to be the same. Okay, so the half-life is always consistent. The amount of time it takes for half of our sample to disappear at the beginning is the same as the time it takes for half of our sample to disappear at the end. It's just that our sample itself is decreasing, right? So here we have 50% of it left, and then we have 25% of it, and then 12% of it, and then 6% of it, and so on, right? And theoretically, this goes until you actually never reach zero, but in reality, you would eventually reach zero, because you'd get down to like one molecule, and eventually that's going to decay or react. It's independent of the initial concentration. So I'm arbitrarily saying that we're going to start at 1, just to kind of make the numbers work out even, but this could be 0.01, it could be 0.067 or something like that. It doesn't matter. The rate of decay is going to be the same if it's a first order reaction. Now there are some formulas associated with this. You can do a natural log of the ratio of what you have at a certain point over what you initially started with. That's the concentration of A sub 0 is your initial concentration. The ratio of that, the natural log of the ratio of that can give you the amount of time. This is kind of where they get this formula. When you simplify this, you get down to natural log of 2, which is 0.693 over K. This is the formula that we're going to be using. This is actually a formula that's given on the formula sheet. So you don't really need to memorize it, but you need to be able to use it. This allows us to figure out a rate constant for any half-life reaction if we know the half-life. The half-life is expressed as an amount of time, right? So it might be a certain amount of minutes, or it might be a certain amount of seconds. Looking at this graph, let's figure out what the half-life is of our sample. Okay, so this is the radioactive decay of element Q. By looking at this, we know it's not zero order, right? Because the concentration versus time should give us a straight line if it's zero order. But we can figure out what our half-life is just from looking at the graph. If we're starting at a concentration of 1, half of that would be 0.5, obviously, and it looks like that's taking basically 3 minutes, a little bit longer maybe. But our half-life is essentially 3 minutes. So what's the molar concentration of element Q after the second half-life has elapsed? Well, if one half-life is 3 minutes, then 2 half-lives would take 6 minutes. And if you've gone through 2 half-lives, that means that you've cut it in half twice. You should be close to 25%, right? And that's essentially what we're at right here. So our molar concentration is 0.25. At what time has 75% of the original sample decayed? If 75% of it has decayed, that means 25% of it is left, right? And so we've actually only gone through 2 half-lives, just like in the previous question. So the first half-life cuts it in half. The second half-life cuts that in half, which now means you're down to a quarter, right? And then if you were to continue from there, you'd go down to an 1/8, and then a 1/16, and then a 32nd, and so on. So this is going to be 2 half-lives, and so it's going to be 6 minutes. All right, let's look at a few more questions. If our half-life is 20 minutes, what would be the rate constant? This is where that 0.693 over K equation comes in really handy. We can rearrange this to solve for K, and then when you plug in your half-life, which is 20 minutes, you end up with your K value, which is 3.47 times 10 to the negative third. In minutes, because our half-life is given in minutes, you could also convert that to seconds. How much time is required for this reaction to be 75% complete? Again, that's 2 half-lives, right? Going from 100% to 50 is 1, and then going from 50 to 25 is a second half-life. And so 2 half-life, if each half-life is 20 minutes, then that's going to take 40 minutes. One more example. If we're given our rate constant, what is the half-life? Again, just take your 0.693 over your K, and that gives you your half-life, which is going to be 12.8 hours. Now, if you were given the half-life, something like this, I would just round this up to 13, because that makes the next question a lot easier. You can actually do this without a calculator. What fraction of the cycle of propane remains after 51.2 hours? If this is 13, if one half-life is 13 minutes, 2 half-lives is going to take 26 minutes essentially, which means that 3 half-lives would take 39, and then 4 half-lives would take 52. Another way you can think about this is just take, if you do have a calculator with you, just take your amount of time divided by your half-life. You get 4 half-lives exactly. So we're going to be going from 100% to 50% to 25%. 3 half-lives will take us to 12%, and a 4th half-life will take us to 6.25%. A lot of the questions you're going to see on this are very conceptual, just kind of working through how many half-lives, and you can kind of just like mathematically go through it, and it's pretty straightforward. All right, this is Mr. Yergler signing out.